Konstantinos, why don't we start just by telling us a little bit about yourself and specifically your journey in quantum. How'd you get involved with it? How long ago? Tell us a little bit more.
Sure. So I started as a physics major, and then I spent many years doing pen testing too. I guess I kind of was trying to hack the universe and computers at the same time. So I always kept quantum computing in the back of my mind because of my physics background, and I knew that it would have serious implications for security, which we'll get to. So when I was at BT for many years, I got to work with Industrial Park Labs, and we were working on QKD, quantum key distribution, and securing that. And I started talking to customers about the threat before the opportunity. So the threat of quantum back in around 2012. So I've been in the industry quite a long time.
Thanks, Konstantinos. And maybe for those, I know this is a topic that many are investing time in, getting more familiar with. But maybe for the benefit of those that haven't spent time talking quantum, in plain English, how does it differ? What's different about quantum than computing today?
Sure. So classical computing, all the von Neumann devices people are used to using, they basically operate in a binary world. So zeros and ones, everything's zeros and ones, and use electricity and transistors to simulate a 0 or a 1 in memory. And that's sort of like the math that people understand, binary. But with quantum, we get to take advantage of some pretty bizarre principles of nature to create a new type of computing entity known as a quantum bit, a qubit. And a qubit can be 0 and 1 at the same time because of a bizarre principle known as superposition. So a quantum particle can be in two states until you make an observation. So once you go from 0 or 1 to 0 and 1 at the same time, a whole new type of math opens up. All types of new algorithms open up to you, and you can do things that are just completely not possible with classical computing.
Wonderful. And I've got a few more questions. We've also got some slides that we'll be sharing after the fact that cover a lot of the topics that we're covering here as well. So those will be available. And please, I told Konstantinos that y'all would try and stump him today. So feel free to put some questions in the Q&A. We're going to try and keep track of those and see if we can't answer a couple as we're talking through things. Konstantinos, many of our clients in the financial services and technology industry specifically are starting to invest and sometimes invest heavily in quantum looking forward. What are some of the key benefits? And we'll get to the security piece in a second here, but before we do that, what are some of the key benefits that firms are looking to realize from quantum?
Yeah, it's important to start with the benefits because it turns out that the kind of machines we have today in this NISQ era, noisy intermediate scale quantum, these machines, even though they're still growing and we're still perfecting them, they can give us benefits before we have to worry about the security risks. So the very first thing that's going to happen is we're going to be able to take advantage of optimization improvements. We've already done experimentation with things like portfolio optimization, where we were able to take what would take 33 hours using traditional classical tensor networks. We were able to do it in 3 minutes using a hybrid classical quantum approach. We can't advertise that as quantum advantage, though, because the accuracy went down a little bit. But once we get those kinks out and improve the accuracy, we're talking about something that would take over a day to run being run in minutes. So portfolio optimization is going to be one of the big ones that we'll see this year as real. Next year, we'll start to see machines come online that cannot be simulated by classical computing. So once that happens, we're going to be able to do things like improve machine learning and improve simulations. So if you're involved in anything like fraud detection or credit scoring, things like that are going to be vastly improved by quantum computing. We're going to be able to do much larger data sets, get much more granular data structures, and really be able to extract interesting edge cases from this data. So if you do any kind of adversarial testing, forget about like really easy acceptance, or let's say with credit scoring, obviously someone with an 800 you're going to accept and someone with a 400 you won't. But when you get to those edge cases right in the middle, that's where quantum computing is going to shine. It's going to be able to make really, really good, solid decisions. And that's true advantage for certain companies. And then we get to simulation for financial services, particularly Monte Carlo simulations. We expect to see consistent quadratic speedups because of the reduced data sets that we'll be allowed to use to still get accurate predictions. So those are just some of the real like high level ones that we see in financial services already. And we're already offering those to customers now as proof of concepts and things that they could start working on.
Exciting possibilities, to be sure. I've got one eye on the clock, Konstantinos, and time is our enemy. But there's a question in the chat that I want to pose to you and see if you can't answer it quickly. You mentioned that quantum is able to live in both a 0 and a 1 state, and in between. And the question is, how do you measure both states at 0 and 1, and any state between it?
So what happens is when you put the qubits into superposition, we don't know what they are, but then you apply gates. So if you think about them as being waves that are kind of like working like this, either constructively or deconstructively working against each other, you pass them through gates, let's say from left to right. And these gates manipulate the qubits. And over time, depending on what algorithm you're trying to run, let's say you were running Shor's algorithm, you'd be concerned with the periodicity of numbers to determine which two numbers make a bigger number, which is of interest for cryptography. You would find that as they pass through each gate, the Z gate, the Hadamard gate, whatever rotations are happening, that eventually you would end up with just a couple of peaks, and those would be your answer. And then you would make an observation on that part of the gate. And once you make the observation, it is no longer quantum. You get either a 0 or a 1. And then because of the structure of the gates, you get your answer. So it could be anything. It could be just pure binary classification of something. It could be which number in the list, whatever you're looking for, but you will get a solid answer. The threat here to building these machines, there's a concept of decoherence. So nature is always trying to make an observation. So that's why quantum computers have to be really, really cold. We're talking almost absolute 0 to make sure that the universe isn't making an observation. Because once something sees your particle, whether it's a human through an observation or just another particle or a temperature or something like that that lets it know what's happening, the decoherence happens and the quantum magic goes away. So it's about that. It's about keeping them in that spooky state of up and down, left and right, however you want to think of 0 and 1. Keeping them that way until you're ready to make your observation and get your answer. Sometimes that could only last a few milliseconds. So quantum computers they're very temperamental still. That's why we call them noisy right now, because they're prone to that kind of decoherence.
Very good, fascinating stuff. So got another good question from Chris Carey, and this leads into the next topic that I want to spend a few minutes on, Konstantinos. You've got a number of cybersecurity and IT risk practitioners on the phone. I imagine they're thinking about what quantum will mean to them. So I'll start out with the question that I hear most, fact or fiction? Quantum will break all cryptography in the future going forward.
Well, it's definitely fiction because there's a whole branch of cryptography called post-quantum cryptography, which is designed to be post-quantum safe. So it won't break that, but it will break things like RSA. Absolutely, it's a foregone conclusion. We knew that since 1994 when Peter Shor worked out his algorithm. We've known since then that when a quantum computer reaches, let's say, about 4,000 quality qubits, ones that aren't susceptible to noise, we will be able to start reversing RSA. And that goes for ECC as well. So other things are in danger, like Bitcoin, seriously in danger right now. It will be possible with just 2,500 quality qubits to start, let's say, setting up a node, listening to transactions, not rebroadcasting them, reversing private keys, and taking money from people. That'll be almost trivial once a quantum computer reaches 2,500 qubits. And with cryptocurrency, it has its own fears because just saying, hey, we think there's a powerful quantum computer will send the prices down to 0. If Elon Musk tweets, I think someone has a quantum computer, it's over. Of course we have quantum computers, but he'll mean one that's sufficiently powerful enough to attack Bitcoin. So yeah, all those communication methods too from RSA, they're in danger. So right now we're very concerned with helping customers with what's called crypto agility. It's this idea, how hard-coded is your cryptography in your organization? Are you writing custom applications where you can't remove the ciphers and replace them? Because NIST right now is working on finalists for post-quantum encryption that will replace RSA. And there are actually solutions you could implement right now if you're worried about long shelf life data. Because remember, things like credit cards, who cares if in 5 years I could play back a transaction from today and get your credit card number? Chances are you don't have that credit card number anymore. But if you transmit the secret recipe to Coca-Cola today, you are going to care if in 5 years I could reverse it. So it's the shelf life of data. So we're already talking to customers about what they can do today to implement post-quantum crypto now to be ready. One of the greatest examples is hybrid post-quantum cryptography, which is used in TLS. AWS pushed hard on this. So what they do, it's kind of clever. They use ECC for part of the handshake, but then they use one of 3 ciphers as a post-quantum element too. And if you crack one, you need to also crack the other. So fortunately for now, we know that Kyber, Bike, and Cyc, all 3 of those are actually supposed to be post-quantum safe.
And is that a good example? You mentioned the word which I've kind of anchored onto, cryptographic agility. Is that a good example of crypto? Easy for me to say.
Yeah, it's funny because crypto agility has been in browsers forever, right? Like sure. You can constantly keep adding, TLS 1.1, 1.2, like you can do that now, and that's like one of the early things you learn with like hacking too. Like, are you running old ciphers? No, these got to go on your website. So browsers have to be ready. That's why you always want a modern browser. So that's a great example of crypto agility. A bad example of crypto agility is like a satellite that went into space 5 years ago and then never even thought about this. And it's going to be stuck with one standard forever. And that's not great once quantum computing becomes more powerful. So whenever you're designing new things now, you want to be in a position that you can bake in that agility, the ability to swap out. And of course, whenever you're doing some kind of new cryptography, the fear is side channel attacks, right? So even though we could prove that these are mathematically okay for quantum computing, we can't prove that the implementation is okay. You hear about this all the time. Like there's something that's supposed to be secure, but you find some other way in. Like when I used to hack quantum key distribution, we were able to mess with the lasers and actually flood the system and fool it. So, so even though, sure, the physics was protecting us because there's a no cloning principle, you can't copy a quantum bit information and move it on, we were still able to. So there's all these other things to consider too.
Very good. John, I think you might be on mute.
Thank you, man. I am always so good with my mute hygiene and then I forget to turn it off. Thank you, guys. Konstantinos, I have to say, listening to you brings back a lot of memories for me because I was a PhD graduate student in particle physics. And I remember using Monte Carlo simulations to figure out where the particles were going to go. And earlier on, I was doing free space laser encoding. So I'm listening to all this going, yeah. And at the time, I thought I would never have to hear those words again. And they would have nothing to do with my day job. I do have 2 questions for you, and I think we have time for both of them. One is you mentioned, that, and I love this, it breaks Bitcoin for sure, which just made me cheer because I think people need to get that. But more broadly, a lot of financial services firms are using blockchain to verify transactions in the back office. Does it break all forms of blockchain as well?
If they have not been designed with post-quantum cryptography in mind, absolutely. Yep.
So basically, financial services folks, if you are looking to adopt blockchain, which you probably should, you need to think in terms of that crypto agility and embedding post-quantum cryptography.
And a great example would be the QRL, the quantum resistant ledger. If you look at what you're doing there, that's an excellent shining example of the kind of work that you can apply to anything else.
And where did they go to see, the viewers go to see QRL?
So for that, you could just go to theqrl.org, I think. That might be
okay.
It. And if not, you could Google it. But I did a podcast episode with them too on my show. So I host the Post Quantum World, and every 2 weeks I talk to someone in the industry about the business impact plus the technology to kind of bridge the world. Yeah.
I think that's wonderful, and thank you for sharing that so people have another resource to go to. Last question that I think we have time for is, you're talking a lot about the hypothetical benefits and so forth. Are there real world examples of post-quantum cryptography going into play other than QRL, which is one, I guess?
Yeah, absolutely.
But real world, yeah.
Yeah, absolutely. We have like third parties that we work with that we can bring in with a customer. And what they do is they choose some of those finalists and they implement them in a way that as it gets narrowed down, they could just remove the losers, let's say, to put it simply. There are boxes that are hybrid. They use QKD, which is physics-based, and also those finalists for ciphers, which are math-based. So you have both options, and then all sorts of like setups just, again, for long shelf life. You don't want to do this for every communication, right? But you do want to do it from now for when you're sending out the Coca-Cola secret formula. And I couldn't bring it up because I'm sure they're not sending it out every day. That's a weird thing to do. Hey, John, how was your weekend? Here's a Coca-Cola formula.
I don't know. Actually, to be perfectly honest, it's kind of scary what kinds of corporate intellectual property is getting sent out. So take your point, but I also take your point earlier about the long lead time or long lifetime transactions that you're worried about. It doesn't matter, some credit card authorization that happened 3 years ago, you have a new credit card.
Healthcare is a good example. Like that kind of information is valuable forever,
Right. Or any kind of PPI, I would imagine, should be protected that way.